Hello and welcome again to my Physics Online Video Lecture Supplement series. In today's video I wanted to talk about statics and equilibrium, which is the 9th set of lectures. This corresponds to the College Physics from OpenStax sections 9.1 through 9.6. In today's lecture I actually wanted to do the first part of that set, which is the first two sections from that chapter in OpenStax. Just call it an introduction to statics. And the basic idea of statics is sort of summarized in this picture of this rock. This rock is actually balanced on another rock. This is not one solid rock. This thing is actually balanced on this guy. The idea is that you have an object whose acceleration is 0, and therefore the net force acting on the object is 0. And that means that although there can be other forces acting on the object, those other forces need to cancel each other out so that you have a net force of 0. You can also have a type of force which acts to twist or rotate. This is called torque. And any of these twisting or rotating forces, these torques, need to also balance out and add to 0. And when you have these two conditions met, you have what's called equilibrium. And so the study of forces and torques in equilibrium is what's called statics. So that's what this set of lectures is about. The first condition for equilibrium I mentioned in the last slide is no net force. First condition basically says that if you take all the external forces on an object and you add them up, you should get a total net force of 0, and therefore an acceleration of 0. For that matter, a change of momentum of 0. So for example, this person in this diagram is at equilibrium because there are two forces which act on him. One is the weight, which acts here at his center of gravity. The other is the normal force, which is acting here from the ground on his feet. If you drew this as a free body diagram, you'd see that the normal force and the weight are equal but in opposite directions, and so the net force is 0. It's basically an application of Newton's first law. The person or object which is in equilibrium is not moving, therefore the acceleration is 0, therefore the net force is 0. And if the object is already in motion, then what we have is a case of what's called dynamic equilibrium, which means the car is coasting with constant velocity, for example, or the person is running at a constant velocity, or so on. And we're mostly interested here, though, in static equilibrium, which is the case where the object is not moving, or where the person is not moving. So in order to have no net force, all the forces must balance along all possible axes. So forces are all vectors. That means that they can be broken into Cartesian components in 2 or 3 dimensions. So for example, these are the forces that are acting on this system. There's a force of tension along this rope, there's a force of tension along this rope, there's a force of tension along this rope. Since the entire system is at equilibrium, that means that the sum of forces acting on this chandelier must be 0. That'd be the weight of the chandelier and then the Fc. But also all the forces acting on this knot or junction where the 3 ropes meet must add to 0. So Fa plus Fb plus Fc must be 0. And you notice that in this one, Fb and Fc are basically along the x and y axes respectively, positive x and negative y. And Fa is the only one that's off at some angle. So therefore you can actually determine how much force is in B and in C based on the weight of this chandelier and based on this angle by breaking Fa up into components, and the x component must be in the negative direction and opposite B. The y component must be in the positive y direction and opposite Fc. The basic condition is that the sum of forces in x is equal to 0, sum of forces in y is equal to 0, sum of forces in z, if you need a third dimension, are also equal to 0. Let's look at an example of this principle in application. Suppose that this chandelier has a mass of 100 kilograms, and of course this is at a 60-degree angle, and this is normal to this other wall. So what are the magnitude of these 3 forces in that case? So from this diagram over here, you can see that FB is entirely in the x direction. So we could write this, for example, as FB, 0. FC is entirely in the y direction. So we call that 0, FC. FA has an x and a y component. So we could say FAX and FAY. and we need for these three forces to add to 0. So basically what that means is that FB plus FA in the x direction is 0, and FC plus FA in the y direction is 0. All right, well, the other thing is that FC must be creating equilibrium for this chandelier. And the chandelier has a weight, which is the mass of the chandelier times the gravitational acceleration. So that's basically going to be 980 newtons. And so we can say Fc plus the weight, or the force of gravity, is equal to 0. Therefore, Fc is 980 newtons. Again, we're just solving for a magnitude there. Okay, so that is Fay. Well, Fa, if we were to split this into components, basically looks like this. So there's a 60-degree angle, here's the 90-degree angle, here's Fax, here's Fay. That is opposite of this angle, so that's going to be Fa times sine of 60 degrees. So Fa, therefore, is going to be given by Fay over sine of 60 degrees. And so that's going to be, in this case, Fc over sine of 60 degrees. Again, we only care about magnitudes here. So that's 980 newtons divided by the sine of 60 degrees. So plug all that into your calculator, and what you get is, here's the sine of 60, and then we need to multiply the reciprocal of that by 980. What you get is 1,132 newtons. So far we can basically write Fa 1,132, or 1,100 since there's maybe only 3 significant figures. Fc is 980 newtons, and Fb is the thing that we have left to find. Well, Fax, you can see, is going to be Fa times the cosine of 60 degrees, because here's Fax, here's the 60 degrees. Cosine of 60 degrees is a half, so we need to take this thing and divide by 2 in order to get the Fb. So divide by 2, and what you get is 566 newtons. So 566 newtons. And now we've got our solution to this problem. That simple example that I just worked through basically illustrates what happens when you have a net force of 0 on an object which is stationary, but notice that we were able to treat the object and the rope, if you will, the junction and the rope, as both being point objects on which the forces are applied. That's not always the case, however. If you have a real extended object that is not suspended from a single point, then it's possible for two forces that are opposing each other to act along different axes on the object. And so, for example, in this hockey stick, in both cases, Newton's first law is satisfied. And so the net force is 0 in both cases. Therefore, there's no translational acceleration of this stick. However, in the second case, these two forces are not applied on the same axis. So even though the free body diagram looks the same for both of these, in this case, the forces are applied at two different axes, and the stick is going to start a clockwise spinning. So we can no longer treat this hockey stick as a simple point object if we're trying to create the condition of static equilibrium. Instead, we have to start paying attention to where the forces are being applied. So the second condition for equilibrium is that there are no accelerated rotations. So that would be equivalent to saying the rotational acceleration is 0. What this requires is that the forces that act on any given object have to be balanced against each other in such a way that not only are they not causing a translational acceleration, but they are also not causing a rotational or twisting acceleration. And these forces which cause a twisting or forces which cause a rotational acceleration are what we call torques. So in some sense, a torque is the rotational equivalent of a force. So our second condition again is no angular acceleration. So as I said, torque is the rotational equivalent of force, and it's given by this equation, which is what's called a vector cross product. A vector cross product works in many ways in the opposite way of the dot product, in that instead of taking two vectors, dotting them, and getting a scalar, you take two vectors, you cross them, and you get a new vector, which is actually going to be perpendicular to either of the two that you're crossing. And so the magnitude of that new vector is given by the magnitudes of the two vectors that are in the cross product times the sine of the angle between them. So here, for example, you see the force being applied at increasingly greater distances from the point of rotation, the axes of rotation. So the torque is getting progressively larger, even though the force applied is actually staying the same from one to the next to the next. So the longer this distance from axes of rotation, the larger the torque for the same amount of force. And what that means is if you wanted to tighten a bolt, for example, you can tighten it by hand for so long, and then if you take a wrench, you can tighten it further. And if you want to loosen a bolt, similarly, you usually start with a wrench, and eventually you can get down to where you hand tighten or hand loosen it. And the reason for that is that if you've tightened using the wrench, you're probably applying that force very far from the bolt head. And so you've applied a lot more torque to this bolt than you're able to muster with just your fingers working on the bolt alone, because that's at a very, very small radial distance from the axes of rotation. And so, for example, if trying to loosen a very, very tight bolt, one trick that is sometimes used is to find a sturdy piece of pipe and to basically put it over the end of the wrench to lengthen the handle out further so that you can still apply the same amount of force to loosen the bolt, but much farther away from where that axis of rotation is. You're basically increasing the value of R while applying the same value of F, and as long as you're pushing perpendicular to this handle, then the sine of theta becomes 1 because theta is 90 degrees, and the result is that you'll have a larger torque, which means greater amount of spinning against the bolt. And so therefore you're able to more easily loosen the bolt. So if we wanted to restate this second condition for equilibrium, we might state it as that when you add all the torques together on an object, they must also be balanced. So adding the vector sum of torques should also give you 0. And if you want to change the torque on an object, you can change basically one of three things ultimately. You can change where a person, you can change one of three things. You can change where the torque is actually being applied, or where the force is actually being applied. You can change how much force is being applied, and then you can change what angle that force is being applied with respect to the lever arm. So in the case of this seesaw, this little boy and this big girl are basically not going to be the same mass, and they're therefore not going to be the same weight. She weighs more than he does. But if she sits nearer to the fulcrum than he does, the system can be balanced. And that's basically, we've changed the weight. We've also changed how far from the fulcrum. So that's 2 of the 3. The third one that could be changed is not really going to be so obviously changed differently for these two. But basically, imagine if you took one of these two arms and you slanted it off at some angle. So the force is still straight down. The radius might be off at some angle, and therefore there's no longer a 90-degree angle between force and radius. So for example, if this seesaw starts to tilt in one direction or the other, the angle between weight and radius starts decreasing, and so the total torque on it starts decreasing, and actually that slows the rate of acceleration of the seesaw. Note that the rate of acceleration may still be positive, so it's still actually speeding up, it's just speeding up at a slower rate. When solving for torques, one thing that you have to do is choose what your pivot point or axis of rotation is going to be. If you have a system which is actually balanced, then the sum of torques acting on that system will be zero at all points. So it doesn't matter where you choose your pivot point to be for the system, as long as it's balanced, you will always get the sum of torques being equal to zero. On the other hand, if you find that the sum of torques is not zero at any given point, then it means that it cannot be zero at any of the points. So either it's zero everywhere or it's zero nowhere within your system. So one consequence of this is that you can actually choose what you're going to use as your pivot point based on what you need to do to solve the problem. So for example, with the seesaw, you might choose the pivot point to be the actual point where the fulcrum meets the lever arms, in which case, torques-wise, this upward force does not count towards the torques, and you only have a torque from this boy in the counterclockwise direction and from the girl in the clockwise direction. On the other hand, you could have chosen the pivot point to be where the boy is, in which case you have a counterclockwise torque by this fulcrum and a clockwise torque by the girl, and the distances at which these are applied are R2 and are R1 and R1 plus R2 respectively. So let's do some examples with that. So let's consider this seesaw that we just have been talking about, and let's assume that the seesaw itself has negligible mass. And we put a 30 kilogram boy on to the seesaw, and maybe the seesaw is 6 meters long from where the boy is to where the fulcrum is. So what is the torque that this boy is exerting in this case? So the torque is going to be given by radius times force times sine of the angle between them. The radius is this right here, 6.0 meters. The force is his weight. Notice that since this is, we're assuming in balance, this means that this is a 90-degree angle, and his weight is going to be his mass times the gravitational acceleration, which is going to be 30 kilograms times 9.80 meters per second squared. So the total torque is going to be 6.0 meters times 30 kilograms times 9.80 meters per second squared times the sine of 90 degrees. So if we throw all of that into our calculator, what we get is 6 times 30 times 9.8, and then of course the sine is just 1. So this gives us a total torque of about 1800 Newton meters. Okay, so let's look at the next example. Suppose that this girl has a mass of 45 kilograms. Where do we need to put her in order for this system to be balanced? All right, if we need for this system to be balanced, then that's the same as saying sum of forces is equal to 0 and sum of torques is equal to 0. Sum of forces is equal to 0 just basically means that we have this upward force balancing the two forces of these two downward. So we basically solve for Fp is equal to Fg1 plus Fg2, or if we want to use the labeling, we could call it weight 1 plus weight 2. Either way, that's going to be M1g plus M2g, or if you throw that into your calculator, that's going to be 30 plus 45 times 9.8. And of course, that 30 plus 45 is just because I've undistributed the g. So this would be 735 newtons that this thing has upward. So 735 newtons. This weight right here is M2g, and that would be 441 newtons. given by, of course, her mass times gravitational acceleration. And then, of course, his weight is going to be his mass times the free fall acceleration, which is going to be 294 newtons. All right, the other thing we need to have happen, though, is that the torques also have to add up to 0. So let's pick a pivot point, and we're going to pick the pivot point to be right here. So the torques basically are going to be, we'll call it tau 1 plus tau 2 plus tau p, which is basically his torque, her torque, and the torque of the fulcrum. Well, if the pivot point is where the fulcrum is, then in this particular choice of pivot point, you have a torque of 0 for that part. And so his torque and her torque need to be equal. His torque is R1 times W1 times sine of theta 1. Hers is R2 W2 sine of theta 2. Since theta is 90 degrees, basically theta 1 is always going to be equal to theta 2 in this case. You can redraw this thing if you'd like. For example, if it's like this, hers would be here, his would be here, and you'll find that this angle and this angle are in fact the same angle, theta 1 and theta 2. So even if it's not 90 degrees, you can still cancel out these sine of thetas. And what you're left with then is that R2 times W2 is equal to R1 W1, or in other words, she should be positioned at this ratio of his weight to her weight times his distance. So that means that she should be sitting 30 over 45 times 6.0 meters away from the fulcrum. And so if you do that ratio, you get 30 over 45, which is 2/3, and then that times 6 should give you 4. So she needs to be sitting 4 meters away from the fulcrum in order for the system to be balanced. This distance right here is 4.0 meters. And then this distance right here, it would be 6.0 meters. Solved. Finally, what happens if we change where we use as our pivot point? So instead of putting the pivot point here, we put it here. Okay, so we're basically moving the pivot point to right here where the boy is sitting. So that means that, again, sum of forces is not going to be affected by moving the pivot point. You still add up this one and subtract them from this, you still get 0. So that part is still true. Let's look at what the sum of torques is doing, though. So you have a downward torque from this weight times this distance, but the pivot point is here. So basically tau 1 plus tau 2 plus tau pivot, or tau fulcrum, I mean. This one right here now goes to 0 because R1 is equal to 0. The R2, we're going to call them maybe R primes. R2 prime is equal to R1 plus R2, which is 6.0 meters plus 4.0 meters, or 10.0 meters. So that's the distance from him to her. And so torque number 2 is going to be R2 primed times weight 2. And so that's 10 times 441, which would be 4,410 Newton meters. Finally, there is the torque from the fulcrum itself. That's going to be R fulcrum prime, or the distance from the fulcrum to here, times the upward force from the fulcrum. So that would be 6.0 meters times 735 newtons. So let's see if this gives us 4,410. So we would have 735 times 6, and you get 4,410. So this is 4,410 Newton meters. And therefore, if you add these up, since they're acting in opposite directions, this one would be a counterclockwise torque. This one would be a clockwise torque. So you basically subtract the two from each other, and what you get is that the sum of torques is equal to this minus this, or 0. So that still checks out as well. One thing that's worth noting here about torques is that you can get a direction for the torque using what's called the right-hand rule. I basically have been saying torque is clockwise or counterclockwise based on whether it tends to make this thing spin in a clockwise direction or a counterclockwise direction. But there's actually a second method for doing this with vectors. Basically, you use your right hand, you point the fingers of your right hand in the direction of the radial vector. So if you started from this pivot point and went to the buoy, you'd be pointing the fingers of your right hand to your left. Then you bend your fingers until they point in the direction that the force is acting in, so down. And the direction that your thumb has to be pointing in order for that to work out is the direction that the torque is said to act in. And so that's why in these diagrams you see a torque that's pointing upward, even though this wrench is going to be spinning in the counterclockwise direction. Basically, if you were to take your right hand, point your fingers of your right hand along the R vector, they'd be pointing down and to your right. Then in order to point them along the force vector, you'd have to curl them up and to the right. And so your thumb would be pointing out of the page if you did this. If you were to apply the force in the opposite direction, you'd still have to have your fingers pointing down and to the left, but now you'd have to curl your fingers downward. And that would be pointing into the page, and that would be the clockwise torque. So counterclockwise torque corresponds to up or positive. Clockwise torque corresponds to down or negative. Since counterclockwise for torque corresponds to upward torque or positive torque, and clockwise for torque corresponds to down or negative torque, it means that torque is actually obeying the same convention for signs as our rotational kinematics terms, namely the rotational velocity and the rotational acceleration. This makes sense, as we will see later when we see what the sum of torques not being equal to 0 gives us, but it also makes sense because we got both sets of conventions using what's called the right-hand rule. I talked about center of mass and how to find it in a previous video. That was basically lecture set 8, part 1, which was on linear momentum. But to recap that, basically if you want to find the center of mass, you take the mass of each individual object and the position of each individual object within your system. You add that product together and then you divide by the total mass of the system. And you can break this down into x, y, and z components. So basically your center of mass looks like x, y, z center of mass. So what the center of mass is actually telling you is you could think of it as the average position of all the mass in the object. The average position of the stuff that makes the object up. And it's a sort of weighted average, and it's weighted by how much stuff or how much mass, how much weight is at each position within an object. So if you have a symmetric object, then the center of mass is located along the axis of symmetry. What that basically means is if you have something like, say, a ball, and you have two balls of the same mass, and you want to know where is the center of mass? Well, it should be exactly in the middle of the line drawn from the center of one ball to the other. We're assuming that the two balls are perfectly spherical and uniform density and so on. If you have 2 point masses, then the center of mass should be right in the exact middle between those 2 point masses. If you have a completely homogeneous object, that means, for example, an object of completely uniform density, and a symmetric object like a ball, for example, or a rod or what have you, then the center of mass would be in that object's exact center. So I gave you on the previous 2 slides ago, or in the previous lecture, a theoretical method for finding the center of mass. It's possible to find experimentally even more easily. What you do is you take a rope or string and you suspend the object from that rope or string. The object will hang in such a way that it will start rotating around until the center of mass is exactly below the suspension point. So you suspend it along one axis, you draw a dotted line from where the rope is to the bottom of the object, straight down. Then you repeat a second time. You hang from another axis, you draw a second dotted line down, and where the 2 dotted lines cross, that's where the center of mass is going to be. Or if you have a 3D object, then you suspend from the 3rd axis and repeat once again. So where these lines intersect basically gives you that center of mass for the object. Let's work an example using the theoretical method. Here I have a system of 3 masses, and I want to know what is the center of mass for this system. So the first system of the 2 systems is this one. There's going to be another one in a little bit. Basically, we're looking for our center of mass, and we notice that there is some symmetry here. The assumption, by the way, is that each of these masses is actually a point mass that's located at the center of wherever the mass is. These numbers here are basically giving you how far from the y-axis is everything. So this one, for example, would be at -1 meter. This one's at positive 0.5, this one's at positive 2.5 meters. And the symmetry of the system is that everything's on the x-axis. So that means that the center of mass, which is at x center of mass, comma, y center of mass, is actually going to be xcm, comma, 0, because nothing has deviated away from the x-axis. So we just need to find the x center of mass. The x center of mass is going to be given by the sum of the x's times the masses divided by the sum of the masses. So in other words, this is saying that we need to go x1 m1 plus x2 m2 plus x3 m3 divided by m1 plus m2 plus m3, where this is 1, this is 2, and this is 3. So that means that we have for our center of mass in x that we have x1 is 1 in the negative direction. So this is negative 1.00 meters times 2.00 kilograms plus 0.500 meters times 2.00 kilograms plus another 2.50 meters times 4.00 kilograms. So that's going in order from this one to this one to this one. And then we have to divide that by the total mass, which is 2.00 kilograms plus 2.00 kilograms plus 4.00 kilograms. So if you plug all those guys in, what you end up getting is, first of all, there's a kilogram in every single term here, so I'm just going to get rid of the kilogram so I don't have to keep writing it. Basically, this means that we have minus 2.00 meters plus 1.00 meters plus 10.00 meters divided by 2 plus 2 plus 4, which is 8. And so negative 2 plus 1 is negative 1 plus another 10 means minus 9.00 meters over 8. And this is our x center of mass. So the x center of mass would be 1.125 meters, or if you look using significant figures here, basically it's 1.13 meters by the time all is said and done, because you have 3 significant figures to work with. So that means that the actual center of mass of the position is going to be 1.13 meters, comma, 0 meters. And that is how you find the center of mass for one of these simple systems. Now let's look at a slightly more complex system in which one of the objects has been moved off of the x-axis, so we no longer have that symmetry. So now what we're doing is we're looking for the center of mass position for this system in which we do not have the symmetry axis that we had in the previous problem. So we would do x center of mass, comma, y center of mass. To get x center of mass, you take the mass times the first x, you take the second mass times the second x, you take the third mass times the third x. You add them together, you divide by this mass plus this mass plus this mass, then you repeat for y. So let's look at that. X center of mass is going to be m1x1 plus m2x2 plus m3x3 divided by m1 plus m2 plus m3. Okay, so this right here is 2 kilograms minus 2 meters. So x center of mass is going to be 2.00 kilograms times 2.00 meters, and it's minus because of what side of the y-axis it's on. Then to that we're going to add 0 meters, so I'm just going to put a 0 there. To that we're going to add 4 kilograms times 4 meters, so 4.00 kilograms times 4.00 meters, and then that is getting divided by 2.00 kilograms plus 3.00 kilograms plus 4.00 kilograms. All right, so our x center of mass is going to be minus 4 plus 16, which is 12.0 kilogram meters over 2 plus 3 is 5 plus 4 is 9, so 9.00 kilograms. And so x center of mass is approximately given by 1 1/3. So that would be 1.33333 repeating. And so since we have 3 significant figures more or less to work with, we might as well just write this as 1.33 meters. Now we do the same thing for the y center of mass. Y center of mass is given by 2 kilograms times 0 plus 1 meter times 3 kilograms, so 3.00 kilograms times 1.00 meters, plus 4 times 0, so 4.00 kilograms times 0 meters. That's going to be divided by, again, 2.00 kilograms plus 3.00 kilograms plus 4.00 kilograms. This is because we need the total mass of the system, 4 plus 3 plus 2. So this means that the center of mass for y is going to be given by 3.00 kilogram meters divided by 9.00 kilogram meters, which is 0.333 meters. So this means that the center of mass position for this system is 1.33 meters, comma 0.333 meters. That means that if we wanted to mark our center of mass position on here, roughly speaking, it would be somewhere in this region, where this right here is about 1.33, and therefore this is about 2.66, so a third of the way. And then this right here should be 0.33 and versus 1.00. So it's about a third of the way up and a third of the way over. Okay, to give a quick summary of the conditions for equilibrium, there's basically 2 conditions that you need for an object to actually be in equilibrium. The first is that you need to satisfy translational equilibrium, in which Newton's first law, or the sum of forces is equal to 0, must be satisfied. The second is that you need rotational equilibrium, in which case the sum of torques is equal to 0. So if you have an object that's in equilibrium, that means it's neither increasing nor decreasing decreasing in its rate of rotation and neither increasing or decreasing in its rate of translation. A totally stationary object is therefore both in rotational and translational equilibrium, and for such an object, all the forces and all the torques must balance. All the forces balance each other, all the torques balance each other. And this is true independent of what axis you choose as your axis of rotation. Therefore, you might as well choose an axis of rotation which can be used to eliminate one or more of the forces from the torque equation if you have multiple unknowns. This is because if you have a force that acts at the rotational axis, then it's going to produce a torque of 0, and that's because if it is acting at the axis of rotation, then for that choice of axis, r equals 0, and the torque is r times f times sine of theta. So I wanted to look at a few examples then of systems that are going to be balanced. So the basic question is, here's a bunch of different systems, and we're going to apply some force to the system, and we want to know how much magnitude of force do we need to apply in each of these cases in order for this system to actually be balanced. So here is system number 1, and the question is, how much force do we need to apply in order for the system to be totally at static equilibrium? Well, you have a downward force of 5 newtons, you have an upward force of 5 newtons. That means that F needs to be 0 in order for the forces to balance. So F is 0 here. Question, are the torques balanced? Well, since these two other forces are at the same position, the torque is balanced. And so that works. 0 newtons is needed to balance the system. For the second one, you have an upward force of 4 newtons and a downward force of 5 newtons. The 4 and 5 are both at the center of mass of the system. So the question is, how much force is needed to balance the system? Well, if this is 5 and this is 4, then you need 1 Newton upward in order to balance all the forces on the system. However, if you apply 1 Newton of force here, you will find that for any choice of axis of rotation, you will not be able to create 0 torque. For example, if your axis of rotation is right here, and this is 1 Newton, then whatever this distance is times 1 Newton is going to give you the torque of not 0, whereas this and this are both 0 torques because they are at the same position. If you put the axis of rotation here, then you have 4 times r minus 5 times r, which gives you minus 1 times r. And r is not 0. So you cannot balance this system. For this one right here, we have 2 newtons up and 6 newtons down. Then we have 2 more newtons up. That means that we need a total of 2 more newtons up here in order for this system to be balanced. So where does here need to, well, again, let's choose this to be our axis of rotation. Then this and this are contributing 0 as our torque. So you have 2 newtons at 4 meters in the counterclockwise direction. That's 8 Newton meters. This is 2 newtons. In order to create 8 Newton meters, you need this to be an upward force that's placed 4 meters away from the center of gravity, or from your axis of rotation. And if you should choose a different axis of rotation, you will find that you still get 0 torque. So for example, if your axis of rotation is over here, 4 meters from this, then you have counterclockwise 2 times 4, which is 8, counterclockwise 2 times 4 plus 4, which is 2 times 8, which is 16. So that's 24 total between this one and this one in the counterclockwise direction. This one is 6 newtons downward, 4 meters away from your axis of rotation, which is also 24 Newton meters. So you still get 0 Newton meters of torque. Option number 4, we have 2 newtons up at minus 2 meters from this position. In other words, 2 meters away here. We have 3 newtons upward here. We have 6 newtons downward here. We need to know how much force and where to put this guy. 2 up plus 3 up gives us a total of 5 up. We had 6 down, so we need 1 Newton up. Now, where do we need to put that Newton upward? Well, this is 2 meters away, and it's 2 newtons. Let's put our axis of rotation here again. So you have 0 torque, 0 torque. 2 times negative 2 is negative 4 Newton meters of torque. So this one has 1 Newton of force, therefore to get 4 Newton meters of torque, we need it to be 4 meters away. So this needs to be 1 Newton upward, 4 meters away and to the right of this center of mass. Next setup, 5 newtons down, 5 newtons up, both at the center of mass. 2 newtons down at 4 meters. Where should this force be? How much? Which direction? Well, there's nothing tricky here other than that this arrow is pointing in the wrong direction. Because forces-wise, 5 minus 5, that leaves us 0, minus 2. So that leaves us with a grand total of plus 2 that's needed. This arrow needs therefore to be plus 2. So the arrow is pointing in the right direction. However, it's on the wrong side of the center of mass. It actually needs to be right over here, right where this arrow is, so that these two are balanced and these two are balanced, and then all the torques and all the forces will be balanced. Last but not least, 6 newtons down, 2 newtons down, 2 newtons up, 2 newtons up. So 2 plus 2 minus 2 is 2, minus 6 is negative 4, so we need 4 newtons for this force. Now, where do we put this 4 newtons upward in order to make this system work? Well, let's put our axes of rotation here again. So these two are contributing 0 torque. Then this one is contributing 2 times 4 is 8 in the counterclockwise. This one is 2 times minus 1 is negative 2. So negative 2 plus 8 means positive 6. So this thing right here needs to be equivalent to negative 6 Newton meters. And recall that this right here had a force of 2 plus 2 minus 2 minus 6, which is negative 4. So we have negative 4 newtons. We need negative 6 Newton meters. So it's got to be 1.5 meters away from this axis of rotation to the left, pointing upwards with a magnitude of 4 newtons. I guess we could call that set of examples the lightning round of examples, but, well, the request was that we have shorter videos, so I cut a lot out of this video to make that work. Hopefully you found this video a little more watchable as a result. I can't guarantee that all of them are going to be this short in the future, but, well, thanks for watching anyway. And I hope